All right, welcome to the Explainer. Today, we're going to pull back the curtain on the one piece of tech that's pretty much powering this entire AI revolution you're seeing everywhere. We're talking about the transformer. So let's just jump right in. I mean, you've heard of GPT, right? We all know it stands for Generative Pretrained Transformer. And yeah, the first two parts are kind of self-explanatory. It generates stuff, and it's been pre-trained on a mountain of data. But that last word, transformer, that T is the real secret sauce. It's the key to this whole thing. Okay, so what is a transformer? Well, at its core, it's a special kind of neural network. It was actually invented by Google way back in 2017, believe it or not, and their goal was just language translation. But now, oh man, it's the engine behind literally everything from ChatGPT to crazy image generators like DALL-E. And what it actually does? Well, it's surprisingly simple. This is the big takeaway right here. You've got this mind-blowingly complex model, billions and billions of moving parts, and what's its number one goal? It's just a prediction engine. Its whole purpose in life is to guess one thing. What's the most likely word that comes next in the sentence? That's it. So when you see ChatGPT spitting out this perfectly written essay, you might think it's magic. But it's not. It's just doing that one simple thing over and over and over again, incredibly fast. It predicts a word, tacks it onto the end of the sentence, and then looks at the new sentence to predict the next word. It's a loop. Prediction plus repetition, that's how you get generation. Okay, so how does it actually do that? Well, your prompt, the thing you type in, it goes on this little journey inside the machine. It's basically a four-step process that takes your words, turns them into math, and then turns that math back into words. Let's walk through it step by step. First things first, the AI doesn't see your sentence the way you do. It breaks it down into these little building blocks called tokens. A token could be a whole word like the, or just a piece of a word like ing, or even just some punctuation. Think of it as chopping up our language into Lego bricks that the machine can actually understand and work with. All right, now this is where it gets cool. Each of those little tokens gets turned into something called a vector. Now, don't let the name scare you. It's just a really, really long list of numbers. And you can think of that list of numbers as a coordinate, a GPS coordinate on this giant, invisible map of meaning. On this map, words that mean similar things, like happy and joyful, end up clustered really close together. Okay, this is what blew my mind when I first saw it, because this meaning space isn't just a random jumble. The directions in this space actually mean something. So you can do vector math. You can literally take the coordinate for king, subtract the coordinate for man, and then add the coordinate for woman, and where do you end up? Right next to the coordinate for queen. It's incredible. It's math, but with concepts. And get this, we're not talking about a simple little 3D map like we're used to. For a big model like GPT-3, each of those word coordinates exists in a space with, wait for it, over 12,000 dimensions. Yeah, I can't picture it either. But that massive, massive space is what gives the model enough room to map out all the tiny, subtle nuances of human language. So where does it store all these coordinates? In a giant lookup table, basically. It's called the embedding matrix. And for this one part of the process, GPT-3 has about 617 million parameters. Just think of those as little knobs and dials that the AI can tweak during its training to fine-tune the map. And that's just our first chunk of the massive 175 billion total parameters in the whole system. Okay, so we've got a coordinate for every word. Great, but you and I know that the meaning of a word changes depending on the sentence it's in, right? So how on earth does the AI figure out the context? I mean, look at this, a fashion model versus a machine learning model. The word model means two totally different things. The original vector for model is the same in both cases. So how does it know? Well, the answer lies in the single biggest innovation of the transformer architecture. It's a mechanism called attention. Okay, attention really is the heart of the whole thing. You can imagine it like this. It lets every single word vector in your sentence talk to every other word vector. They all kind of look at each other and say, hey, who here is important to my meaning? The model vector sees the fashion vector and says, aha, and then it adjusts its own meaning based on that context. It literally soaks up the meaning from the words around it. And it doesn't just do this once. It goes through layer after layer of this attention process. By the time you get to the very last word in your prompt, its vector has absorbed the context from everything that came before it. It's not just a vector for that one word anymore. It's a super condensed mathematical representation of your entire thought. So now we have this one super powerful context-rich vector. What do we do with it?
Well, we do the opposite of what we did at the beginning. We run it through a final matrix called the unembedding matrix. And its only job is to take that one vector and project it back out across the AI's entire vocabulary, all 50,000 plus tokens, and give every single one of them a score. In this second matrix, this unembedding one, it's just as huge as the first one. We're talking another 600 million or so parameters. So now our running total is over 1.2 billion of GPT-3's 175 billion parameters. And what's crazy is we haven't even gotten to the main guts of the network yet. This is all just the bookends. But the output from that last step, it's not very useful yet. The fancy word for it is logits, but really it's just a raw, messy list of scores for every possible word. Some scores are positive, some are negative, they're all over the place. It's not a nice, clean probability distribution we can work with. So to clean up that mess, the model runs all those scores through a neat little mathematical function called Softmax. And what Softmax does is it takes all those wacky positive and negative scores and transforms them into a beautiful, clean probability distribution. Every score is now between 0 and 1, and the whole thing adds up to a perfect 100%. Now we can see exactly which words the model thinks are the most likely to come next. And this is where a bit of human control comes in. There's a setting you can tweak called temperature. Think of it like a creativity knob. If you turn the temperature down low, the AI will almost always pick the single most probable, most predictable word. But if you turn the temperature up, it starts to get a little more creative, a little more adventurous. It might pick the third or fourth most likely word, leading to some really interesting, unexpected results. Okay, so let's do a quick recap of that whole journey. Your prompt gets broken into tokens. Those tokens get turned into vectors, which are just coordinates on a giant map of meaning. Then the magic of attention lets those vectors talk to each other and soak up all the context. And finally, that one super contextualized vector is used to predict the probability for every possible next word. It's a beautiful flow, from language to pure math, and then right back to language again. But here's the thing that's so wild to think about. Every single step we just talked about, it's just math. A whole lot of it, sure, but it's just multiplying giant tables of numbers together. There's no understanding chip in there. Which leaves us with this really big, fascinating question. At what point does 175 billion simple calculations start to look and feel like actual understanding?